Okay, welcome everyone to my continuation of what is algebraic graph theory. Today would like to talk about the properties that are true for almost all graphs. So think of the problem that you put all graphs in a large bag. Ignore the fact that it's of course not possible, but we put them all in a large bag and we draw out one randomly. Can we say whether it has property X, property Y, property Z? And the point here is kind of the takeaway is that the easiest property kind of all graphs, in the sense of almost all, share is that almost all graphs have really a large number of edges, like a lot of edges, like a lot of edges. So kind of just the flavor is that properties that are easy to satisfy with a lot of edges should be somehow true almost all of the time. And remember that almost all of the time doesn't mean always. It's just always in a quotation mark sense. It's like really literally, well, in practice it's always, but it's not literally always. Anyway, so what I will do, or what I've done here, I listed all graphs up to 18 vertices, and I ask how many of them are connected. So I take the ratio connected graphs over all graphs for a fixed number of vertices. And yeah, as you can see, it fairly quickly grows. And essentially here, what is it, 95% or something for 18 vertices down here. So recall or note or observe that most graphs have, I'm not quite sure how you can observe that. Probably you can yourself, but anyway, most graphs have many edges. So connectivity is clearly related to having edges, and the more edges you have, the more likely it is to be connected. So almost all graphs should be connected. Yeah, and kind of this is a proof, if you want, that this really works. So I think this is kind of a really nice way to do this. So you would kind of run this up to a certain number of vertices. This is a clear pattern, and then you would kind of try to go and prove it. And of course, in this case, maybe not of course, but in this case, you can actually formally prove it. Right? I hope this is clear, right? We have many edges. So every property which has many edges has a good chance to, which is easy satisfied with many edges, has a good chance to be true for almost all graphs. And connected is clearly a property that is easier satisfied if you have a lot of edges. So that should be true for almost all graphs. And by magic, it is, right? So does it make some sense, I hope? So we are looking for properties that are kind of easy satisfied with many graphs, with many edges, or on the contrary, we are also looking for properties which are hard to be satisfied with many edges. I will have an example later on. So many edges, so actually right now, later on, yeah, right now. That's very good scripted here. So absolutely perfectly scripted. Anyway, many edges part 2. So recall that we have many edges. I hope you're not surprised by now. And being planar, so being drawable in the plane, is so like this one here, you can draw it in the plane, is clearly a property that is difficult to satisfy if you have many edges, right? So I kind of suspect I have a problem with my code because the spike here. But anyway, the overall pattern is kind of clear. I do the same as before. I list planar graphs over all graphs, again, up to 18 vertices. And this goes down to about 0.2%. So this is kind of what we scale. This is not 0, this is 0.4 here. But anyway, there's an absolutely clear pattern, and it's not difficult to prove that as well. Let me say it again. I hope you're not confused by now, or you're not surprised. We have many edges. There's a property that is difficult to be satisfied with many edges, namely being planar. And so this should be kind of wrong, right? It should not hold for almost all graphs. So almost no graph should have that property. And yeah, you can convince yourself by doing it by hand if you want. You probably only will go up to something like this. Or ask a machine, and it will go up a little bit further. And eventually you can actually write down a proof that this is true. I hope I make some sense. Next property, or a mixture of properties. Recall that we have many edges. Surprise, surprise. Anyway, so here are two properties of graphs. One of them is easily satisfied with many edges. The other one is difficult to be satisfied with many edges, namely whether a graph is Hamiltonian or Eulerian. And I just did the same here. Hamiltonian goes to 1, Eulerian goes to 0. So remember that Hamiltonian means you have a path in your graph that visits every vertex exactly once. This is a very boring one, but anyway, every vertex once, right? Vertex 1 doesn't make any sense. Vertex once. Okay, so that's clearly easily satisfied with many edges, because if you have many edges, you have many possibilities to go around, right? So, and it turns out that almost all graphs are Hamiltonian. A kind of the dual property in an Eulerian graph, you would, well, again, a very boring example. So let me put in some extra edges here, and the green one is a pass, whatever. I probably don't want should do that. Yeah, whatever. That's fine. So let's put another edge here. Good. So in the green one is a pass. So in a Hamiltonian, in an Eulerian graph, you are supposed to visit every edge exactly once. So here is something where you visit every edge exactly once, but it actually doesn't matter whether you visit the vertices multiple times. Right? So visiting every edge exactly once is very difficult if you have many edges, right? Visiting every vertex exactly once is very easy if you have many edges. And yep, exactly what you would suspect, I hope by now, suspect what happens will happen. So almost all graphs are Hamiltonian, but almost no graph is Eulerian. And yeah, you can then go and actually prove it. So yeah, there's a proof. And let's say we are talking about the random graphs again, and there are better statements. You can vary P, but let's fix the probability. And it doesn't matter how small the probability is. Remember, the probability is the coin flip probability, whether I put an edge or not. As soon as n is very large, there will be many edges anyway. And almost all of them are connected, almost all of them are not planar, almost all of them are Hamiltonian, and almost no of them are Eulerian, exactly like we have seen before, right? As I said, there are also things for varying P, but they're a little bit more difficult to write down, so I will do that. And it's somehow a little bit surprising, even if you have really, really tiny probability, like you only put an edge with 0.01, well, only in every 100th case. As soon as n is very large, you still have many edges. That's kind of the point. The only thing I can't allow is 0, obviously, because if I put edges with probability 0, then my graphs won't have many edges. But otherwise, everything is fine. And I think that's a really cool theorem, actually, right? So you have 3 things that are either easy or difficult to be satisfied with many edges, and they indeed hold for all graphs. And the way we do that, to say that they hold for, almost all graphs, is that we kind of prove it for a random graph, which is really just we put all graphs at the back and we pull out something randomly. That's a very, very nice theorem. I think that's really, really great. And then there are, again, properties that I'm going to show you later, which are not so easy to decide whether they're actually difficult or hard with many edges. For example, how big the automorphism group of a graph is. And it turns out there are some really, really strange flaws, really, really strange patterns. So for example, the size, this is a really nice table. So the size of the automorphism group, so it's trivial, it's of size 2, size 3, whatever. And as you can see, 3 is really difficult to satisfy, right? Count the number of graphs with that automorphism group, but it starts off as 0, 0, 0, 0, 0, 0, 0, 0. And I don't guarantee that I got all the zeros correct here. Anyway, so it has 9 vertices. The smallest graph with an automorphism group of order 3 has 9 vertices. And it's already quite large. And order 2 does but much better. And other orders like order 8 is much better. So there's some really strange kind of bias here in what happens. So it's a bit strange. And I will explain that in the next video. The only thing that I can guarantee that if you should take out from this video already is that almost, because there are so many edges, there can't be so many symmetries. So almost all graphs have trivial symmetry group. And it takes a while to get started, but you can see that here in the table. As I said, it takes a while to get started, but eventually here, this number is by far the largest compared to the 4, for example, and it will just grow out everything else. So here's a property that is a bit difficult to decide, and it kind of gets very interesting, so kind of very subtle and interesting. But kind of the overall flavor, there are many edges, so essentially there should be no symmetries, and by symmetries I mean automorphisms of the graph. Anyway, slogan today, in case you didn't get that, let me repeat it, there are many edges, so properties that depend on edges are kind of easily graded by whether they're almost always true or whether they are almost always false. And I think that's pretty cool, and you can really prove that. That's kind of the point of this random type graph theory. Anyway, I hope you enjoyed this video, and I also hope to see you next time.